Hello everyone. Today we are going to talk about hydrocarbons. Everything about hydrocarbons. Starting from alkanes, what are the basics and the properties, how it is prepared, where it is used, and followed by alkenes and alkynes. Also, we are going to talk about aromaticity, which is one of those important questions in any competitive examinations. And most importantly, as I told you in the last video, we are going to talk about electrophilic substitution reaction, guys. It is super important for any organic chemistry reactions. So without any further delay, let's get started. Let's start with alkanes. So alkanes with the formula CnH2n plus 2, which means it starts with n is equal to 1 and goes like this: 1, 2, 3, 4, 5, 6. And also we know the simplest hydrocarbon, that is methane, CH4, and then comes C2H6, C3H8, and goes on. Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. So talking about alkanes, we can't get rid of this isomerism part. We already talked a lot about isomerism in different types. Here in hydrocarbons chapter, we just have this straight chain isomers, structural isomers only. But if you want more about isomerism, I'll be linking the isomerism video in the description or in the I button. Please make use of it. Okay. So talking about isomerism, it is as simple as that, which will have same molecular formula but different structural formula, that is called structural isomerism. And for example, here I am going to take hexane. Simplest hydrocarbons, you can work on it. I am just taking a 6-carbon system, which is hexane. So how can I write hexane in different ways? How can I write the different isomers of hexane? CH3, CH2, 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 CH3, that is N-hexane. Okay. So what is the molecular formula of hexane? That is C6, 2N plus 2, which makes it H14. So another way of writing it, by replacing one of those hydrogens with CH3. So CH2, CH2, CH3. So what is the molecular formula of this? Which is once again C6H14. And the name of this isomer is, the second position I am having methyl group. So 2 methyl, 5 carbons in the parent chain, so pentane. Correct? Then another way of writing hexane, 6-carbon system, can I place it in 3rd carbon? Yes, I can. So which makes it as 3-methyl pentane. So don't think of it replacing the 4th carbon, then it will become 2-methyl pentane once again, because we have to give the lowest number for the substituents. Okay, so what about combining these two? CH3, CH3, and CH3, and then CH3. The second and third position I am having methyl group. So 2, 3 dimethyl In the parent chain I'm having 4 carbons, so which makes it butane. What if I'm writing it as a tertiary carbon? CH3 on the same carbon. So total 4 and then CH2, CH3. What is the name of this? Which is 2,2 dimethyl. 4 carbons in the parent chain. So which makes it once again butane. Okay. So these are the isomers of the molecular formula C6H14. Okay. So once we know the isomers of straight chain isomers, let's move on to conformations. Conformations are again the spatial arrangement of our atoms which can be converted into another arrangement by a rotation. By rotation we are changing it. The rotation must be a single bond. Okay. We can't rotate the double bonded system, which is very strong. It's tend to break. So we are just rotating this single bond system. C bond C, which should be a single. What are you telling, ma'am? I got confused. Don't worry, I got you covered. Take an example of ethane. So ethane, the formula is CH3CH3. Carbon with 3 hydrogens. Once again a carbon with 3 hydrogens. Okay. So how can I write it in case of Newman projection? This is one carbon and the dot is in another one. So I am writing the hydrogens for this carbon and hydrogens of another carbon. Okay, so here you can see the angle between the substituents, the hydrogens, are very less. This type of conformation are called eclipsed. Eclipsed. And what about another rotation, another 60-degree rotation of one of those carbons? So what will happen? I'm keeping this carbon as such. I'm just rotating the another carbon to 60 degree, which will give you the conformation like this. This conformation is called staggered. Comparing eclipsed and staggered, which is more stable? Always staggered is more stable than eclipsed. Why? Because there will be more strain on the angle of eclipsed conformation is very less than the staggered. Always there should be some space for each one of them, right? So staggered is more stable than the eclipsed conformation. Okay, so that's about isomers of alkanes. So what about their physical properties? There won't be much question asked about physical properties, but it's better to know. Talking about hydrocarbons, talking about alkanes, as the number of carbon atom increases, the boiling point or also increases because the molecular weight will get increased, so the boiling point will also get increased. What about if I am having a branching like we saw in 2,2 or 2,3, that more than that? What if I'm having more branches? So higher the branching, lesser will be the boiling point. Okay, which makes it occupies a small lesser area and the boiling point will get decreased. Say for example, if I am taking hexane, compared it with 2,2 dimethyl butane, then boiling point of 2,2 dimethyl butane will be lesser than the hexane. Okay. If I am talking about melting point, melting point is always depend on the packing. So if that is closely packed, there is no much space between them, then the melting point will be higher. If there is more space, then the melting point will be lower. That is the whole idea of melting point, whatever the compound you can take. So the melting point increases with the number of carbon atoms, but increases, which will also increase the melting point when we move an even numbered alkane to next odd numbered alkane. The melting point will get increased. Okay. So let's move on to the more interesting part, that is preparation of alkane. If you are thorough with this hydrocarbons chapter, the 12th chapters like haloalkanes, alcohols will be a cakewalk to you. Okay, so please concentrate on your basics, please concentrate on your reaction mechanisms, what type of substitution, additions or eliminations can happen. That is more important than memorizing those mechanisms. Okay, so coming back to the topic, preparation of alkanes, the simple preparation just we take first, that is from carboxylic acid. Carboxylic acid, we very well know the formula of carboxylic acid is RCOOH. Here I am taking it as a salt of carboxylic acid. Say for example RCOONA. I am going to dehydrate it using calcium oxide and the temperature is 630 Kelvin. In the presence of base, this is happening. So I'll form RH with Na2CO3. Right? So just a substitution had happened over there. RH, which is an alkane, has been formed. What if I am taking RCOOK in aqueous? This reaction is very important. This is called Coles electrolysis. Anode part oxidation will happen and the cathode part reduction will happen. You can just go through those things, but end of the reaction you will get R with R. Okay, higher order alkanes can be prepared from this method, which is produced at anode part. That is very important. At anode your end product, the desired product has been produced. That is from carboxylic acid salts. As a second preparation, from alkyl halide. I told you, right? Haloalkanes chapter will be easy for you. From alkyl halide. Say for example, I am taking Rx, treating it with 2 moles of Na. 2 Na means I have to use another Rx or XR. You can write it in either way. Presence of dry ether. What can happen? You know that very well. RR will be formed along with that 2NaX. You can take any halogens to do this reaction, and you'll be getting a high order alkene. So that what you can conclude is that preparing methane, it's not possible using this method. Okay, and if I am taking a different alkyl halide, what can happen? For example, I am taking Rx with 2 moles of sodium with R-X. So the reaction conditions are same. If I am taking a different alkynes, so I'll be ended up with R dash along with that 2NaX. But the yield will be very less. Why? Because there will be a chances of forming R as well or R dash as well. So which makes the yield is very less. This type of reaction is named as Woods reaction. It's one of those named reaction. We'll be revising this in Halo chapter as well. So please mark this as an important Woods reaction. Okay, let's move on. What if I want methane production? I want RH. What I have to do? In that case, you can treat Rx with palladium carbon, or you can go with nickel hydrogen, or you can go with copper zinc, zinc with HCl, zinc with NaOH, anything works. Basically with a catalyst, reduction catalyst, so that hydrogen will get added to produce RH. So what are the things I have told? Zinc with HCl or zinc with NaOH, or you can take nickel with hydrogen or copper with zinc. I'm just mentioning it as common, but you can use any one of these. Okay. Then the third preparation of alkanes involves from hydrogenation. What is hydrogenation? Addition of hydrogens. So you can add hydrogens from alkene or alkyne. Say for example, if you are taking RCH double bond CH2 and I'm adding the nickel catalyst along with hydrogen with the help of heat, so each one of those hydrogens will get added across the double bond. So end product will look like RCH2CH3. Similarly, you can go about with alkyne. The end product will be RCH double bond CH2. And once again, if you are giving hydrogens, it will take 4 moles of hydrogen. 4 hydrogens are 2 moles of H2 to proceed this reaction to get alkane. Okay, then the next preparation is that, don't worry, only the alkane preparation is more, and then alkene will be less, alkyne will be very, very less. The next preparation, that is from reduction of alcohol or carbonyl compound, reduction method. So always you have to remember one thing, by reducing ROH, in this case I am using, it's depend on the alcohol I am taking and the catalyst as well. So here I am using ROH, I am generalized, but the reagent I am going to use is HI with red phosphorus. The reagent is very, 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 very important, guys, for this reduction. HI with red phosphorus, we will be dealing with this in biomolecules chapter as well, but in case of glucose and fructose, here also we are using it to make alkane. What about aldehyde? So in case of aldehyde, I am using again HI with red phosphorus, or you can use zinc amalgam with acid condition, or you can use hydrazine with basic condition. So zinc amalgam with acid condition, which refer to as Clemmensen reduction, and this part, if you are using hydrazine with a basic condition, then the reaction is referred to as Wolff-Kirschner reduction. Okay, so I told you aldehyde chapter, we will see that. Here the formation of RCH3. What about if I am using carboxylic acid? Carboxylic acid with HI with red phosphorus, heating will give you RCH3. The next method, that is hydrolysis. Hydrolysis using Grignard reagent. So Grignard reagent, guys, who don't know, that is a versatile reagent. It is very, very important in synthetic organic chemistry, and this is an organometallic compound, which means that metal with organic compound, metal with alkyl groups. RMgX, that is a Grignard reagent. X can be of anything, any halo group. So I am treating Grignard reagent with water. Of course, this is hydrolysis. Always remember, wherever the lysis word comes, that means for part, that means for cut, separate. Okay, hydrolysis means H2O will get separated as H plus and OH minus. You can remember it like that. So R will take up hydrogen and remaining OH will go to Mg. Then the last preparation is that from hydrolysis of carbide. So carbides, let's take B2C. I'm treating it with water. This is an hydrolysis. So what can happen? CH4. How many carbons you are using, that much. Okay. Irrespective of the carbon you are using as a carbide, you will get CH4. For example, if you are using Al4, C3, you will be ended up with CH4. And the reaction is that R with R dash or R, any R with R2CuLi, which is again a organometallic compound, presence of dry ether, which will produce R dash with R dash. So variant alkyl group. This synthesis is called Corey-House synthesis, and reagent R2CuLi is known as Gilman's reagent. Okay, so Corey-House synthesis, Gold's electrolysis, Clemmensen reduction, Wolff-Kishner reduction, and whatnot. These are the things we are seeing in Wood's reaction. These are the things we are seeing it in preparation of alkanes. So what I suggest you to do is, whenever you are starting an organic part, try to write all those named reactions aside, because most of the questions in organic can be asked from named reactions. Okay, so whenever you are studying about the named reactions, write it separately in your notebook. Okay, so let's move on to the chemical reactions of alkanes. So alkanes, which is a saturated hydrocarbon, so which can undergo what kind of reaction? It can undergo substitution. Yes, it can. The substitution, as I told you, we already discussed very briefly about the type of substitutions in the last video. Here, in case of alkanes, let me take CH4 as a simple compound with Cl2. In the presence of UV or sunlight, it produces CH3Cl with HCl. How can I remember it? Yes. Here, what is the mechanism behind it? Why this is giving this product? This substitution, mostly you can remember wherever the substitution happens with HNO or sunlight or UV light, that happens with the mechanism of free radical substitution. So what is free radical? We discussed it. It is one of those intermediate that is having a unparity electron in it. Right. So free radical, it is highly reactive. So what is this mechanism of this kind of free radical substitution? This follows three processes you can take. The first process is chain initiation. Apart from other substitution reactions, this is bit different. This is bit different and interesting too. Chain initiation. So for that, I'm taking Cl. I just used Cl2, right? So I'm taking Cl, bond Cl. What happens? Homolectic cleavage happens, which means that each one of those atoms will take up one electron from the bond, since it is a covalent bond. And always, free radical mechanism must be written with the fish hook arrow, like this. It forms 2Cl radical. Okay. Then the step 2, that is chain propagation. Chain propagation. Propagation means continuation. What happens next? I took methane, so I'm writing it like this as a displayed formula. This methane, I told you free radicals are highly reactive. So one of those chlorine radical is reacting with methane. How? So it leaves like this to form a bond. So CH3 with the radical and HCl is formed. Is it a only way in the chain propagation? Why can't it be this CH3 radical reacts with another Cl? Yes, that can happen. So CH3 radical with another Cl radical come together to form our end product. But this is chain's termination process. So I'm going to keep that below for now. Let's analyze what are the other ways of chain propagation can happen. Say for example, CH3 with the radical which formed in the chain propagation can react with ClCl to form CH3's Cl with Cl radical. Okay. So this kind of propagation means it never ends. Only if that ends, then that is a chain termination. Termination means ending, is it? So in case of initiation, the radicals are formed. In case of propagation, one of those products can form along with the radical formation. In the termination, all those radicals are come together to form and get settled with the product. But the main drawback of free radical reaction is that if that follows free radical mechanism, then the yield will be less. Yield is nothing but the end product, the desired end product. Why the yield is less? It's because of the mix of products can be formed. Mix of product formation. Okay. So It can be mixed, like CH3 radical combines with Cl radical to form CH3Cl, and then you can find it out like CH3 radical combines again with another CH3 radical to form an higher alkane. That is also possible. Or Cl radicals again combine to form Cl2. That is also possible. So mix of products are forming, so the desired product yield will be very less. Okay. Then the next reaction is nitration. So nitration, I am taking ethane, HNO3 in the presence of 423 to 673 Kelvin heat. One of those hydrogens are getting substituted by NO2. The remaining product will be water will be leaving. Along with that, an interesting part that can be CH3NO2 can be formed. So the substitution and lead to once again the more than one product. The third part, that is sulfonation. Here we are using H2SO4, but the problem is only from 6-carbon system it can undergo. It can undergo sulfonation. For example, C6H13 with hydrogen that may get replaced or substituted by SO3H. So C6H13 with SO3H. Then the next reaction, that is oxidation. Oxidation means we very well know addition of oxygen can happen. So here I am taking CH3 in the presence of CH3COO twice Mn. Where the oxidation happens, it will give acetic acid as a end product along with the elimination of H2O. What if I am taking a tertiary alkanes? So for example, like this. I am treating it with strong oxidizing agent Ka1O4, which will give CH3COH, CH3CH3. It is only possible for tertiary alkanes. What will happen if there is only one carbon, ma'am? For example, methane. Will it undergo oxidation? Of course, yes. Each one of them deserve a chance. So here I am treating it with carbon tube at high temperature and pressure conditions. It will form CH3OH. And if I am treating it with molybdenum oxide with the same temperature and pressure, I am getting a aldehyde along with water. So compare the reactions. Methane oxidation with copper tube, that will give you alcohol. Same methane with molybdenum oxide, that will give you aldehyde. So compare and study, that will be easier for you. Then this next part, that is isomerization. Isomerization We already saw what is isomers are. For example, here I'm taking butane, N-butane. As an isomer of N-butane, I'm getting CH3, CH, CH3, CH3 with the reagent that is more important. That is none other than anhydrous aluminium chloride with concentrated HCl. By the application of heat, I am getting isomers of the straight chain alkanes. Then comes pyrolysis. So pyrolysis, which is nothing but heat reactions. So CH3, CH2, CH3. I'm treating it with high temperature. Always the pyrolysis wants high temperature. Any catalyst you can use to speed up the reaction. What will happen? Elimination is happening over there to give different alkenes. For example, 3 carbon as a propene, and you can get ethene as well, methane as well, and hydrogen as well. Okay. Then the last reaction, that is aromatization. We'll see what is aromatic compounds are. Aromatization is formation of aromatic compound. I'm taking C6H14 as an alkane and treating it with chromic oxide or vanadium pentoxide or molybdenum oxide at high temperature and pressure, not so high, but 770 Kelvin, 10 to 12 atm pressure. Let's say I'm taking vanadium pentoxide. Once again, you can take chromic oxide or molybdenum oxide as well. I'm getting as benzene. It is one of those important preparation of benzene. Please note it down. That's it about alkanes. Now we are moving to alkenes. So alkenes, which will have double bond compound, double bond is a p pi b pi bond once again, and which is sp2 hybridized, linear in structure, which can exhibit isomerism as geometrical isomerism. What is that? I told you in alkanes, conformations means the rotation of single bond. It can't rotate the double bond. Yes, that is true. In case of geometrical isomerism, we are taking a linear double bond system, but the twist is each carbon across the double bond should have different groups attached to it, like this. So if I am having a compound like this, it will not undergo geometrical isomerism. The two groups must be different. The two groups attached to one carbon must be different to exhibit geometrical isomerism, which is super important. Okay, some questions can be asked to find which of the following can exhibit geometrical isomerism. So please be careful with this part. Okay, so talking about isomerism, the two groups should be different, and If the same groups, for example H and H, CH3, CH3, Cl, Cl, so both the groups are on the same side, then this isomer is cis. Or if both the groups are on the opposite side, for example like this, then that is called trans. Okay, which are having same molecular formula and structures, but they are having different configurations. So due to that, what will happen? The trans isomer, which will not have a dipole moment, but the cis isomer can have the dipole moment, and the boiling point of cis isomer is more than that of trans isomers. If we need more about the geometrical isomerism, we have an already video on this. Please watch it. Let's dive into preparation of alkenes. The first preparation, that is dehydrohalogenation. What is dehydrohalogenation? D means eliminating the thing, hydro, hydrogen, halogenation for halogens. So which makes it an elimination process. It is a beta elimination. What is beta, ma'am? So beta part, that is where the substituent or the functional group is attached from that the near carbon to that carbon. For example, here I am taking CH3, CH2, Cl. So this is alpha carbon where the functional group or the substituent is attached, and this is beta. So beta elimination happens, and always remember, in case of elimination, use alcoholic KOH, not an aqueous. Always use alcoholic KOH. Alcoholic KOH undergoes elimination, aqueous undergoes substitution. So Cl and one of those hydrogens will get eliminated to give CH2, CH2 plus HCl. Similarly, dehydration, which means hydrogen can be removed, that is CH3, CH2OH if I am taking. Once again, this is a beta elimination. I am using concentrated sulfuric acid, OH, and one of those hydrogens will get removed to form a alkene. Third preparation, that is dehalogenation. Simply dehalogenation, which means halogens will be removed. Say for example, I am taking vicinal chloride. Vicinal means same groups attached on the adjacent carbon. Geminal is the same carbon. Zinc, which will end up with alkene along with that Cl. The next preparation, that is partial hydrogenation. This reaction we already saw in Alkanes preparation from alkyne. If I am taking alkyne and doing the partial hydrogenation, let's say I am using hydrogen with palladium, BaSO4, which will give you CH2, CH2. This reagent is for the preparation of cis alkene. Okay, Here you can't find cis and trans, but in case if you have taken R C triple bond R with this reagent, you will be getting C double bond C R R. This is an example for cis alkane. So what if I want trans? Then change the reagent, sodium with liquid ammonia. I'm getting a trans alkene. So this reaction is called bridge reduction. Bridge reduction always give you trans alkene, and the former one which produced the cis alkene, the reagent is palladium hydrogen with barium sulfate. Here the barium sulfate is acting as a poisonous catalyst. Okay. Then the final preparation, that is Gold's electrolysis. We already talked about Gold's electrolysis, where at anode we produced the alkane. Similarly, here we are taking 2 carbon system with a carboxylic acid salt. Electrolysis, it is producing CH2 double bond CH2 at anode. Now we are moving to physical properties of alkane. We have discussed it earlier, the hydrocarbons. The first 3 members of hydrocarbons of alkenes are gases, the next 14 are liquids, and the higher ones are solids. Higher the molecular mass, the compound will become more solid. And they show the regular increase in boiling points as the molecular weight increases and size increases. Every CH2 group added to the chain increases the boiling point by 20 to 30 Kelvin. So that is our physical properties. Now we are diving into chemical properties. Chemical properties of alkenes. The first thing, alkenes undergo electrophilic addition reactions. Electrophilic addition. We already talked about what is addition reactions and what are the mechanism it follows in types of reactions video. Here this is undergoing electrophilic addition, which means, for example, if I am taking CH3 CH double bond CH2, treating it with HBr, so HBr will get added up to the double bond. So it will form a compound like this. Here you can get a question, ma'am, where Br will go, where hydrogen will go. So that leads to the rule which is called Markovnikov's rule. Which states that during electrophilic addition to alkene, the most stable product or the major product you can take, most stable product formed via most stable carbocation. That is our Markovnikov rule. I would like to define it in another way, which is you can remember it easily. That says about rich getting richer, which means that if I am taking any HBr, HCl, HF, HI. So any electrophilic addition reagent, the hydrogen part, the positive part will go to more number of hydrogens. Let's say here hydrogen is positive, Br is negative. So hydrogen goes to where more number of hydrogens are there. Here the more number of hydrogens belongs to CH2. So hydrogen goes to CH2. Okay. Or else you can remember it like negative adenine will join to the more substituted carbon. You can remember it in any way, but you should remember it. Okay, that is about Markovnikov's rule. What about if I am having peroxide with HBr? This kind of combo. I'm taking the same molecule, but here I'm taking peroxide along with HBr. In this combo, particularly HBr peroxide combo will lead to anti-Markovnikov rule. It's just opposite to Markovnikov's rule. So the product, major product, why I'm mentioning major product is because the another one which becomes minor. In case of first example, this product is minor, and in case of second example, this becomes major and the first product is minor. So the major product, that is a more stable carbocation, that is for Markovnikov rule. In case of peroxide with HBr combo, then it will lead to anti-Markovnikov rule, which is also known as Karash effect or peroxide effect. But that holds true only for this combo, HBr with peroxide combo. Okay, then what are the other chemical reactions alkene can give? I just listed out this in this way. Let's see one by one. The first one, which is hydrogenation. Hydrogenation, that will lead to give you hydrogen got substituted, got added to the double bond. So CH3, CH3. And this second one, X2 with CS2, which will lead to the addition of X on both the carbons. Both the carbons are across the double bond. And HX, as we discussed earlier, Markovnikov's rule. And the next one, H2SO4. Here you can see H and OSO3H. So that is our H plus and OSO3H, it is minus part. Then the point to be noted, that is cold KMNO4, cold alkaline KMNO4, that leads to formation of glycol and this is a syn addition. Syn addition means both the groups are added on the same side. Syn addition, and if I am using hard KMNO4, that will lead to the formation of CO2 with H2. Okay, then peracid. Peracid means CH3COOH. Okay, so peracid with oxygen and silver, that will lead to the formation of epoxide, and then again followed by the hydrolysis, it will give you the anti-addition of OH groups. which will get added on the opposite side. Then comes ozonization, which lead to the formation of formaldehyde. Here I am having only 2 carbons. So formaldehyde has been formed. Whenever you are dealing with ozonolysis with double bonded system, the simple trick you can follow is that just put double bond O, break the double bond, put double bond O, write the product HCHO. Okay, if I'm having something like this, then again break the bond, put double bond O, write the product as CHO plus HCHO. Okay, that is ozonolysis. And then mercury salt with sodium borohydrate, which lead to the formation of alcohol, that is called Markovnikov addition with the reaction is called oxymercuration demercuration. The next important reaction is that hydroboration followed by oxidation with BH3 or B2H6, whatever the dimer also they can give, with DHF as a solvent, which lead to the formation of alcohol, but here it is following anti-Markovnikov. Okay, so the next reagent, that is S2Cl2, which is giving us Cl, CH2CH2 with sulfur. It is known as mustard gas. Okay, so that's it about the reactions, chemical reactions of alkene. Now we are moving to alkynes. So alkynes, we know that very well, which is a triple bonded system. For example, acetylene, and the hybridization is sp, so which makes it more electronegative, more the s character, more electronegative. What would be the preparation of alkyne? So the first preparation, you can prepare it by hydrolysis. So let me write the alkene in the middle so that it will be easy to memorize. The first preparation, that is hydrolysis of carbides. So CaC2, treating it with water, which will lead to the formation of acetylene or any other, depend on the carbide, the triple bond will form. For example, if I am taking Mg2C3, then this won't be the product. The product is CH3 C triple bond CH for the hydrolysis. The second method of producing acetylene or triple bonded system is that dehydrohalogenation. Once again, that is a beta elimination process. I told you alcoholic KOH we have to use from CH2Br, CH2Br. Dehydrohalogenation happens with the elimination of 2 HBr molecules. Then, if I am taking CHBr2 with CHBr2, reacting it with zinc metal, with heat, it is producing a triple bond system. That is, the reaction is called dehalogenation, because halogens are getting removed. The next preparation is that from alkyl halide. For example, if I am taking HC triple bond CNA, the next very important preparation is that HC COOK. By seeing itself, you may guess the reaction. That is, yes, you are right, that is Gold's electrolysis. Okay, so these are the 5 important reactions to prepare alkynes. So what about its properties? What about its chemical reaction? Means, as you can see, Cl2 can react with acetylene to give CH2Cl, CH2Cl, and then if I am adding HCl, that will get added up to 2 moles of HCl, means I will get CH3CHCl2, which follows the addition process, and HOCl, once again 2 moles of HOCl, that will give you CHCl2, CHO, aldehyde is forming. H2SO4, I told you that separates as H plus and OSO3H minus, so that will get added. Mostly these alkanes are giving addition reactions. In this case, dilute H2SO4 with mercuric sulfate, it is giving us aldehyde. Oxidation happens, and then barium cyanide, addition of HCN, hot KMNO4. Point to be noted, hot KMNO4 in case of alkenes that gave CO2 with H2O. Here 2 CO2 has been produced, and in case of cold KMNO4, alkenes gave us alcohol with the syn addition. Here it is forming acid. And K2Cr2O7, once again oxidation happens to give acetic acid, and ozonolysis that leads to a formation of CHO. In case of ozonolysis, I told you in alkenes, break the bond and put double bond O. Here, just to break 2 bonds only, have 1 bond with the carbon and do the same. Put double bond O. You will get the product. That's it about alkynes. The next thing, very interesting thing, that is aromatic hydrocarbons. Aromatic. What is aroma? Aroma is a good smell. So these aromatic compounds are having very good smell, and which is very, very stable. For example, our benzene, our naphthalene. Okay, so these are some aromatic hydrocarbons. Here, while naming it, you have to consider one thing. In a benzene ring, if I am having a substituent, for example, I am having a substituent as CH3. From the substituent, I am numbering it 1, 2, 3, 4, 5, 6. Second and 6th position are ortho. Third and 5th position are called meta positions. And the 4th position is para. Okay, this thing you need to remember. Why I am saying this? Because if I want to name this, according to the functional group priority order, OH gets more priority. So the overall Without NO2, the compound is phenol. So in the ortho position, I'm having nitro. So I should name it as orthonitrophenol. Okay. Similarly, you just try to name for this one. Okay. Let me know the name in the comment section. Okay. So aromaticity. What are the rules must be followed to find whether the compound is aromatic or not? The rules are very simple. Rule number 1, that is, the compound should be planar and ring, or you can take it as a closed system. Rule number 2, that is, the compound must have the complete delocalization of pi electrons. Delocalization of pi electrons. And most importantly, the number of electrons used in the delocalization must satisfy 4n plus 2 pi electron rule. Here n is equal to 0, 1, 2, 3 and so on. Okay. Say for example, if I am taking benzene, there are 6 electrons. So complete delocalization of pi electron, which means this bond goes here, this goes here, this goes here. So it just completed the ring. So it didn't stop anywhere, or it is having a conjugated pi system. Okay, what about number of pi electrons? Here this is having 6 pi electrons. Will that satisfy 4n plus 2 pi electron rule? Let's check. If I am substituting n is equal to 1, then I'm getting 6. So 6 electrons in benzene. So it satisfies 4n plus 2 pi electron rule, which also called as Huckel's rule. Any other examples can you tell me for aromatic compound? Yes, I can. For example, a system like this, which is closed and planar, that is having 2 electrons in it. It can undergo delocalization. It is having 2 electrons in it. So which means if I am substituting n is equal to 1, you will end up with getting 2. So which is also aromatic. You can try out with these compounds. You can include lone pair of electrons as well while doing this delocalization, because that can also involve in the electron delocalizations. These are some aromatic compounds. What if a compound that is ring, planar, but it is not satisfying 4n plus 2 pi electron rule, Huckel rule, but it is having other qualities, other criteria: complete delocalization, conjugated pi system, ring, planar and everything, but just it is not satisfying this rule, then that is considered as anti-aromatic compound. Anti-aromatic compound which should satisfy 4n pi rule. Then that is anti-aromatic. I'll be attaching a sheet which is aromatic, which is anti-aromatic, which is non-aromatic, and why that is so. I'll be attaching that sheet in the description. Please do check out If you're getting any confusion in aromaticity, that sheet will be very, very helpful to you. Okay. Now let's move on to the preparation of benzene. The preparation of benzene, which is having 7 important reactions. The first one, I'm treating acetylene with red hot temperature, which will end up with benzene, and phenol with zinc dust will give you benzene. Benzene diazonium chloride with H3PO4. This is most important reaction. This reaction can be combined with other reactions to ask as a JEE main and NEET questions as well, even in JEE advanced. Okay, so the next one, COONA, sodium salt of benzoic acid, treated with NaOH to give benzene, and then hexane. N-hexane with chromic oxide and alumina. At higher temperatures, it will lead to the formation of benzene. And sulfonated benzene, upon hydrolysis, it is giving us benzene. And chlorobenzene, nickel with aluminium reduction in the presence of base, that will lead to the formation of benzenes. Then we are going to look the properties of benzene, chemical properties of benzene. You can see benzene is a very reactive and versatile compound, but at the same time it is more stable. It undergoes many reactions. As you can see, benzene can take up chlorine to form chlorobenzene, take up nitro group to form nitrobenzene, sulfonation it can undergo, alkylation, acylation. So you can see these 5 are electrophilic substitution of benzene. So in case of electrophilic substitution, it follows a mechanism of formation of electrophile and attack of electrophile and formation of the products. But one thing should be clear. Here we are using AlCl3, which is a Lewis acid, which is having a vacant orbital in it, which facilitates the electrophile formation. Since it is having a vacant orbital, let's say I am having Cl2, it will accept the electron so that Cl plus will be formed. So that acts as an electrophile to attack on benzene. Okay, so these are electrophilic substitution, and these two particularly called as Friedel-Crafts alkylation and acylation. Alkylation and acylation. Then other reactions with vanadium pentoxide, it is forming an anhydride, and following ozonolysis, it is giving us aldehyde, and treating it with chlorine with sunlight, it is forming as hexachlorohexane. 6 chlorines are getting substituted over here. What are the other reactions of benzene? Includes, it can undergo reduction using granate nickel. That is most important reaction. Usually benzene will not undergo reduction unless or until the reaction is very strong. So in this case, we are using granate nickel with hydrogen to form cyclohexane from benzene. So all of these reactions of benzene is super important. Okay. Then another important category in the types of reaction video I just told you, we'll see about this electrophilic substitution of benzene in detail in hydrocarbons. As I promised, here I'm going to tell you how this direction happens, whether that is going to ortho, whether that is going to para or meta, how it compound decides it. Okay, so how it influences the direction. The first thing is, if a compound, if a benzene ring is having a substituent which is electron donating group. What is electron donating group, ma'am? For example, if I am taking NH2 which is having a lone pair which can be donated, or NHR, OH, OCH3, NHCOCH3, or alkyl groups, methyl, ethyl and all alkyl groups. So these are some electron donating groups. What that will do? How the electron donating affects the benzene influence of incoming electrophile group. So electrophile, which is an electron rich substance. Electrophile, which is an electron deficient one, which attacks the position where that is electron rich, right? So due to the presence of these electron donating groups, as you can see in the resonance, in the structure, this ortho and para positions are having a electron rich place. So it leads to the incoming electrophile to ortho and para positions. So the incoming electrophile will attack ortho and para positions if a benzene ring is having a electron donating group. So what if that is having a electron withdrawing group? For example, nitro, cyano, aldehyde, or COR, or you can take carboxylic acid, COOR, SO3H. These are some electron withdrawing groups. It withdraws the electron from the benzene ring. So which leads to the electron rich position on meta side. You can see electron deficient site is produced on ortho and para. So comparatively, meta becomes electron rich. So which makes incoming electrophile to attack meta position. Okay, say for example, if I am having nitro and this is undergoing electrophilic substitution reaction, then the incoming electrophile is what? Nitro group, is it? So that will lead to the meta position to the existing substituent. What if I'm having a CH3 group on the benzene ring and I'm undergoing nitration? I'm doing nitration on it. What that will produce? Since CH3 group, that is an electron donating group, which leads to the formation of orthopara substituent products. Okay, so comparing ortho and para, most of the cases para becomes more stable and major product than ortho. So that's it about this hydrocarbons chapter. We have seen a lot. So please read mindfully, do the practices as much as you can. We'll drop the exams. Practice, practice, practice.